Hey friends, it is Ben again. This is a video to help you get going with, got a pop-up that says something about set up professional audio. Yeah, guess not. I'm sorry. So this is a video that's supposed to help you all get going with the assignment for Friday, 28th of April. The assignment we're looking at has to do with linear regression. So I want to try to talk a little bit about what linear regression is and what we're actually doing with it. Okay, so as per usual, I'm going to share screen here and we will see what's going on. All right, so you should be seeing here my notebook that y'all will be working from that says basic ideas of linear regression. So the basic notion here is that you have a set of data. In the picture, it should be the green dots, okay? So the green dots is a set of data that we think should fit onto some particular function. Now, in our case, we're going to fit a straight line to it. But I need you to understand that the word linear in linear regression doesn't mean the straight line. You can fit a parabola or sines and cosines. You can fit any functions like this. But the easiest example to see is the straight line. So that's what we're going to start with. All right. So we're trying to find a straight line that we think this data should have been on. We're assuming that there might be some sort of measurement errors or something going on with it. And so the method that we have for doing this actually comes from linear algebra. If you haven't done linear algebra, do not worry. All the linear algebra that you need to know is contained in what we're doing here, okay? And it's relatively straightforward. But in linear algebra, you have equations that you try to solve of the form ax equals b, and where a is a matrix, x and b are both vectors. But in this case, we have the matrix A being determined by functions. Yeah, determined by functions at the given data points. So it's functions of the x value. Okay, so you have that matrix there. And then you have instead of the x vector, you have, sorry, the camera noticed that I was using my hand and tried to put my hand up. Instead of an x vector, it's the a being multiplied by the set of coefficients that you got. And wish I knew how to put my hand down. Okay, I can't. Sorry. So the matrix A determined by functions that you're trying to fit times the coefficients and is equal to the y values that you're trying to do something with here. And it generally turns out to be something that you can't actually solve. And what you do is to take the matrix that you got there, the A, take its transpose and multiply that at the front and multiply that on the left of the vector that's over on the other side of it. And then it turns into a system you can solve. And so you do. So that's what's actually happening under the hood here. You don't need to worry about that. What you need to worry about is what the input is going to be. Okay. So, oh yeah. So in that diagram there, the thing for you to notice is that the line we're getting is going to miss these points because the points generally don't line up perfectly in a straight line. They have some sort of errors from being off the straight line. Okay. And what the process that we've got of this linear regression does is it minimizes the total length of those little dashed lines there. So here we see we have what, 5, 6 points, right? And it literally takes and uses the geometry of the situation to find a line that minimizes the total out of that. It's kind of neat. You can also think of it in terms of calculus, but I think doing it that way is super duper overrated. The geometry of linear algebra is a much better way to see it. So that's my advertisement for linear algebra. So then I go ahead and talk about that there. Yeah, blah, blah, blah. Then here is the first example that we have, and I've stolen it directly from this website. Okay. But if you look in that, what it's got is your import statements from NumPy, which we've been doing, but then also from this sklearn setup, and I don't know what the SK stands for, sorry, but it has a linear regression package in it. There's also a linear regression package in Skippy, and there's probably one in NumPy as well. So I would invite you to take a look at those and see if you can figure out how to use those better than you can figure out how to use this. But this one seemed to be fairly simple. So I thought it would be a good one to have us look at. We are also then going to be doing some plotting here. So we'll have to import the things for that. So then the thing that I've got here is my X and my Y are just made up numbers, okay? Generally speaking, you will not type those in because usually the X and Y arrays that you have will be thousands of numbers long. You just can't type them in. What you will in general be doing is reading them out of a file, okay? But this example, we can see the numbers, and that makes it kind of nice to see what's going on. So the points in question are x equals 5, y equals 5, x equals 15, y equals 20, x equals 25, y equals 14, x equals 35, y equals 32, x equals 45, y equals 22, x equals 55, y equals 38. Okay, so there's 6 points on the graph. I'm not sure if they're the same 6 points from the graph we saw here a minute ago or not, but this command here at the end should be new to you, and it is something that takes and reshapes our array to be what we want, okay? As we'll see when we come down here and have it print out X and Y, Y is an array that is just a row array, so, but the X array here, it wants it to instead be a column. And the way it represents that is to make each row its own little array of one thing in it. Okay. So you need that particular shape in order to make the stuff work right in this. So we get the X and the Y there, and it had to reshape the X. And I don't know what to tell you about that. That reshape command does what we need. Later, we'll use a different command to do the reshape because I don't know. And yeah, I don't know what to say about that. Okay. But it prints the X and the Y. And then here on this line, model equals linear regression dot fit of XY. So linear regression is the object that we have read out of the sklearn library. And we have a method for it or a function for it that will make the fit if you feed it the data that we've got, the X and the Y, okay? And the X needs to be a column vector and the Y needs to be a row vector. But once you've got the model there, it uses score as the method to read out the read out the R squared value, which is the sorry, we haven't talked about the R squared value. There is a score that comes along with any linear regression model that we refer to as R. R is a measure of how well correlated the data is. If the data is I hope that I'm drawing this in the air the right way. If it is a upward slope perfect line, you would get an R value of +1. If it's a downward slope perfect line, then you get an R value of -1. In between those, the closer it is to a perfect straight line, the closer you get to 1 or -1. The more scattered and spread out it is, the closer you'll get to 0. Okay. But we often go ahead and square the R value because it makes it convenient to go ahead and say R equals 0 is uncorrelated and R equals 1 is perfectly correlated. Sorry, R squared equals 0 and R squared equals 1. Okay. So anyway, for whatever reasons, they use score to read that out there. And then there are also these things you read out, intercept underscore. I cannot tell you why it has an underscore. That feels weird to me, but it may be that it allows you to do something. Yeah, it probably allows you to do something with arrays and vectors and stuff, but that gets complicated. We're going to try to stay basic. Then coefficient is going to be the coefficient of your x value. So if you think about y equals mx plus b being a straight line, the m, the slope of the line, that's your coefficient. The b, the y-intercept, that's your intercept. Okay. And so we go ahead and read those out there. There's another piece that I'll say something about in a minute about this prediction stuff, but this went ahead and printed out here that we had a coefficient of determination about 0.7159. That's fairly strong, but not super strong. Okay. Then this intercept of 5.6 and the slope of 0.54. If we went ahead and drew y equals 0.54 times x plus 5.63-ish, it would look about like that. Okay. And then this bit here that I promised to talk about model.predict. It alleges that you can plug an x value into it, and it will go ahead and figure out the mx plus b for you. I was mystified because when I plugged something into it that was a number instead of a vector, it gave me an error. So I thought, oh, it needs a vector. I gave it a vector and it gave me an error. So other than feeding the x back to it, I don't know what the purpose really is. So, but I used that in order to draw the little red dots here. Those red dots are then the predictions of what the y values would be. Okay, so what's this used for? That would be a question that you maybe ought to think about. When we talk, and now that I have that, I can hopefully lower my hand. Yay. Yay. Okay. So when we have these, this sort of a model figured out, and bear in mind, it might be not a linear model. There's applications of this where it's not straight lines. But you have something where you have some way to make guesses and predictions about something in the future. If you have taken an economics class and you talk about demand function curves are something that's kind of nebulous there, and they always treat it as linear, but it's not particularly linear. It could be anything as long as it has a downward slope to it. But it's convenient to be able to do something with a linear function for it. So they collect a bunch of data. They try selling the I don't know, seashells at the seashore for $5 and see how many they sell, and they try selling them for $8 and see how many they sell. Maybe, you know, a few more points there, and then they can get a scatter plot, and they can do a linear fit to that. Once you've got that linear fit, like we've got here, you can plug your demand function in to get your profit function. And because the profit function then will have a peak on it, you can figure out what the X value is that gives you the maximum profit. So it allows you to do optimization stuff that you couldn't otherwise. There are plenty of other applications, but they end up being a little bit abstract. If you do certain kinds of modeling that takes seasonal stuff into effect, you can actually use other techniques to factor the seasonal changes out. And so we can spot trends like, climate change, the increase in global temperatures, because we can factor out the seasonal changes. So anyway, I'm afraid I'll have to ask you to take my word for it that there's other applications to it. But that's just, you know, some places that this comes up. Okay. So let me jump back over here to the screen and let's talk a little bit about what we're doing for problem number 1. So in problem number 1, I went ahead and went to Kaggle.com, which is a website with a lot of machine learning data sets. And the data set that I found was, what was it called? A salary data set. And it related the number of years experience that a person had in some particular industry or geographic area. It didn't give that information. But it related X and Y values there for us to do linear regression with. So the thing I want you to do is to load it. I've already provided the link and everything there. And then go ahead and hit and put a code cell in there and say df raw so that you can actually see what the data looks like. And the 2 columns, one of them is going to be for years of experience and one of them is going to be for salary. So read those out and put those into NumPy arrays, okay? And do the manipulation in order to get them the same shape as we saw in the previous example. Now, with regard to that, you are going to need to use .t, okay? So say you have read dfraw in there, you can say x equals np.array parentheses dfraw square brackets and then the tick marks and whatever the name of the column is for the years experience. Say it's years. But at the end of your parentheses out there, if you'll say .T, it will put the array into the shape that you're needing here, okay? If you don't put the .T, then you will have a row vector, whereas you need a column vector. The .T just trades rows for columns. And for the Y, of course, you're going to go ahead and read that in, and you don't need to take the transpose, okay? All right, but otherwise you should be able to run this in there and print out what your coefficient is and what your intercept is. And I literally just want you to go ahead and plug in x equals 15 and see what you come out with, okay? And then maybe if you've got the inclination to do it, poke around and see how you put number formats in there so that it looks nice. You can see a dollar sign and commas and crap like that. Okay. So, all right. So the next bit here is we're talking about multiple regression. Multiple regression just means that you have multiple factors in here. So in the example we're going to look at, or the example I'm going to have you look at, I think it's sales revenue as determined by ad revenue in 3 different settings: newspaper, TV, and radio. Okay. So this one here that we've got an example worked out for doesn't really have an explanation of what's going on. Hang on a sec. Sorry. It doesn't really have an explanation of what's going on, but it has 2 variables that are affecting it. So in this case, it has the x1 is 0, x2 is 1, and those are associated with the y value of 4. 5,1 is associated with the 5. 15,2 is associated with the 20. Get the idea? Each pair that you've got there for the x's determines exactly 1 for the y's. And as you'll see here with the printout, this has taken the x's and it has just typed them in. And it has put them in such a way that you've got 2 columns on this array. Okay. And then the y values is just 1 row. You go ahead on this and turn them into numpy arrays. And then we do the same sort of thing with it. Okay. Like before, we do the linear regression, and we have to tell it to fit things for the x and the y. And the x needs to be taller than it is wide, and the y needs to be just wide without any height. But the score is this r² variable again, and the intercept is going to be the intercept like before, but the coefficients may have multiple entries here for them. So the particular thing that we had here was that we got 0.447 something, and we got 0.2502 something, right? So if you were using these, you would have 5.5226 plus 0.447 something x1 plus 0.2550 x2. That would be your model. And so if you wanted to predict what you would get out for this x0, x1, called them x1, x2, sorry. If you wanted to predict what you got for that, you would just plug them in the places that it shows it up here. I plugged in a 10, a 20, and I plugged in a 10. Okay, that's all that's going on with these. So what we've got is that Python is doing all of the work behind the scenes of finding out what those coefficients are, and then you've got those numbers and you can use them for whatever purposes you have. So here in problem number 2, I go ahead and, you know what, I'm going to go ahead and open that up. This is the data that I have. It has a TV, can I make that bigger? Yep. TV ad budget column, a radio ad budget column, newspaper ad budget column, and sales figures for some product that's being advertised. So you can go ahead and read that in there. And I went ahead and said dfraw.columns here so that I could see what the different columns are. but you are going to want to tell it that this does get tricky. So I'm going to actually do this part here and show you what it is that's going on. It takes a second for it to load, but I am going to want to say my X is equal to, I believe it's NP array parentheses square bracket DF tick mark TV ad budget. You know what? I'm just a bad typist, as those of you who've had calculus with me know. And I am going to put that in there like that, comma, BF, tick mark, get the radio ad budget. And we'll put that in there, comma, DF, tick mark, newspaper ad budget. Put that in there. Okay. And I believe I just need the dot T at the end of that. Dot T, not comma T. So let me tell it to show me X so that I can. Oh, it gave me an error. What was the error? DF is not defined. Well, of course it's not defined because it was not named DF. It was named DF raw. What was I thinking? Should have just named it DF. Okay, does that get it? Yeah. Now you can see what it looks like there. It's an exceedingly tall column and stuff, but your trick is that you're going to need to tell it it's a numpy array, square brackets, df raw, square brackets, and the names of the columns. Okay. So I am going to be a big meanie and erase that and leave it to y'all to see what to do on that. Okay. For the Y, it does not need to be transposed and stuff. Look back to the previous example, okay? And you'll see that there's a difference on this. Okay, but in any case, with that, you're going to run this regression, and then, oh, I did a problem here with the, I bet I need to say slash to get that to work right. Is that better? Yeah, okay. So you're going to perform linear regression once you get the coefficients. Then you're going to try to predict the sales for a product that only used $50 on the radio advertising, okay? So that means for call them X0, X1, X2, one of those is going to be 50 and the other two are going to be 0, okay? And depending on which order you put things in, it might be any of them, right? And then also, I want you to predict it for if they took $75 and evenly divided it between the 3 of them. I'm going to leave that to you to figure out what I mean by that. It's not deep. It's just what you think, okay? But predict what will they get out of that. Bear in mind with this that it's got everything in dollar sales. So surely they meant it to be in thousands of dollars or something. I don't know though. But you're going to come along here, plug in, see what you get, write a little text code cell and say something about what you're getting out as a result. I want you to get practiced at writing actual words, okay? But tell me what you end up with out of that. Then the last thing we're talking about here is polynomial regression. What this means is instead of fitting just y equals mx plus b, you might be fitting something like y equals ax squared plus bx plus c. Or it might have cubics or fourth degrees or something. For what we're doing, we're just going to do second degree, but you can do very high degree sort of things on these. All right. And it's done a little bit differently, but not that much differently. So again, the examples I'm pulling from, I came from this realpython.com site. Please, if you want to understand more about linear regression, go read that website. They have a much better explanation than the super short get it done thing I'm telling you. Okay. But anyhow, though, this example here has, in addition to the linear model stuff, has the pre-processing setup of polynomial features. Okay, so it's just got a little extra thing on it. So when we come along here, just like before, we're going to have points like x equals 5, y equals 15, x equals 15, y equals 11, so on and so forth. So these are really just one set of x's and one set of y's, but the whole thing is set up so that they're paired together. Okay. And we still had to reshape them the way we did before. I don't know why they didn't just use .t. So, but I was stealing somebody else's example, so I just left it the way they had it. Anyhow, once we have that x set up, then it makes an x underscore. I don't like that name, but whatever. So the x underscore, it feeds to polynomial features. Degree is 2, so we're doing a second degree polynomial, a quadratic. Include bias equals false. So the include bias equals false means not to include the coefficient. Yeah, I'm sorry, not to include the intercept on this. If you don't include the intercept on this, it will push the intercept over to the coefficients matrix. Okay, so we'll see what's going on with it in a second. But you probably want to go ahead and say to include bias. You probably want to go ahead and put the include bias equals false for what you do as well. All right. But then we have this fit transform here that goes ahead and tells it to do something to the x so that it's set up the right way. Okay. If you went ahead and print out that x underscore, you will see that it will have a column of ones, a column of that's just the x's that you had, and then a third column, which would be the squares of those. So anyway, our model then, we fit not the x and y, but the x underscore and y. Okay. Relatively straightforward thing, but just remember that we're fitting with the x underscore because of the fact we're doing a polynomial fit. Then, like before, we can get the score, the intercept, and the coefficients. And when we see those printed out here, I am mystified. I have said to include bias equal false. And so the intercept didn't turn out to be 0 like I thought. Well, that's weird. Okay. You got me. I don't know what's going on. So the having false there doesn't fit with my intuition of what this means. So in any case, though, we have taken these and fit them in there. And our fit has a 0.8909 for the R squared. That's pretty strong, okay? And then our intercept of 21 point something, our coefficients then here. So the fit that we end up with is going to be y equals 21 point something minus 1.3 times x plus 0.03-ish times x squared. That's what we've got. And then if you needed to plug in an x value, you literally would just plug in the x value and calculate. Okay. So your problem is to pull this data here, this data related the BMI, that's body mass index. It is a number that doctors assign that's supposed to tell you how fat somebody is. Okay. I, for example, am sitting right at a BMI of 30, which is the line between overweight and obese. So it seems a little odd to me. Obese seems a cruel word, but whatever. But they're relating the BMI to blood pressure. Okay. So you are going to, again, read this data in. You're going to pull it off for your X variable, make your X underscore variable the same way as we did here, fit it, and see what your model looks like. And then once you see what the model looks like, plug in the numbers 15, 20, 25, and 30. Okay. As best as I recall, I think 15 is in the underweight sort of score, and 20, yeah, somewhere around 20 is fit. I was once fit briefly, didn't last long. So, yeah, so plug those numbers in and report what you get. So, as usual, make a little text code cell and type out what you ended up finding out from it. Okay. Somebody who already finished this commented to me that it turns out that the R squared value is really small. So you would think that body mass index and blood pressure score would be closely related, but maybe they're related in non-linear sort of way or in a non-quadratic sort of way. I don't know. If you have any questions, go ahead and ask them. I'll see you all tomorrow.